There's a moment, and rangers who have worked at Yellowstone long enough all describe it differently, but they're always describing the same thing. When the park stops feeling like a park, when the ground beneath your feet stops feeling like ground, it doesn't announce itself with any obvious warning. It's more like a shift in temperature that you notice a second too late, or a sound that sits just below the range where your brain decides to pay attention. Something that makes the back of your neck feel strange. Something that makes you want to stop walking and just listen. A backcountry ranger named Jeff, who spent years patrolling the zones around the Norris Geyser Basin, once described feeling the change in his legs before any instrument picked it up. Not shaking, not anything dramatic, just a low, steady hum rising up through the soles of his boots, like standing beside an enormous engine that was idling. Patient, contained, waiting. He said he started trusting that feeling more than any equipment, not because he was superstitious, because the feeling was always right. He wasn't wrong to trust it, because that's exactly what Yellowstone is, a massive hidden engine. Underneath the meadows and the elk herds and the waterfalls and the boardwalks full of tourists pointing cameras, underneath all of it, something is alive. Not metaphorically, not poetically. Literally alive in the geological sense. A magma system of extraordinary scale sits below the surface, pumping heat upward with a consistency that has continued for millions of years without stopping once. The Yellowstone caldera, the collapsed remnant of a supervolcanic eruption that happened 640,000 years ago, stretches roughly 34 miles by 45 miles. It is not a mountain with a crater at the top, which is how most people imagine a volcano. It is a depression. A scar in the landscape so enormous that most visitors drive through it for hours without realizing they are inside it at all. The mountains they see at the edges are not the walls of a volcano. They are part of the collapsed rim of something that, in human terms, is almost too large to imagine. And here's the thing that doesn't appear in most travel guides. The ground above that caldera is moving. It has been moving for as long as anyone has been measuring, and in certain places, it has been moving faster in recent years than in any period since systematic monitoring began. In some sections near the Norris Geyser Basin, the ground rose by as much as 7 inches over the course of just a few years, then subsided again, then started rising again. Scientists call it uplift and subsidence. The rangers just call it breathing. And when the ground breathes, things on top of it change. Hot springs shift. Geysers that hadn't erupted in decades suddenly wake up. Boardwalks that were built over stable ground begin to sit above patches of earth that are now 30 degrees hotter than they were the previous year. Roads buckle. Trees that have stood for generations begin to die, not from insects or disease, but because the soil temperature around their roots has crossed a threshold that no root system can survive. And animals notice all of this long before any human does. In the spring of 2014, something happened that got a lot of attention online and very little serious coverage. A video surfaced, shot from a car window near the north entrance of the park, showing a large herd of bison running. Not walking, running, moving fast along the road away from the interior of the park. People watching the clip immediately started speculating about what it meant. Was this an animal response to impending volcanic activity? Were the bison fleeing something the rest of us couldn't feel? The clip spread quickly, and the narrative attached to it was dramatic. But what actually happened is, in some ways, more interesting than the narrative. The bison weren't fleeing. They were doing what bison do in early spring, moving toward food, toward lower elevations where the snow melts first, following routes they have used for centuries. The footage showed normal behavior, filmed from an angle and at a speed that made it look like escape. But here's the thing that got lost in all the noise. Some researchers who study animal behavior at Yellowstone noted that, in the weeks surrounding that footage, there had been a measurable uptick in earthquake activity beneath the park. Small earthquakes, nothing felt by people at the surface, but a genuine cluster. And the question that nobody fully answered was whether the animal movement patterns during that same period were random, or whether something in the behavior of the herd was slightly different from baseline, not fleeing, but perhaps alert in a way that defied easy measurement. Because that's the problem with Yellowstone. So much of what happens there sits right at the edge of what we can measure and explain. The instruments are good, the scientists are rigorous, but the system itself is so complex, so layered, so ancient, that the data often produces more questions than answers. And the questions that can't be fully answered have a way of accumulating. Take the geysers. Most people know about Old Faithful, which has become a kind of national symbol, reliable, predictable, photogenic. What's less widely known is that Old Faithful has been slowing down, not in any dramatic or alarming way. But when researchers looked at historical records going back to the late 1800s, they found that the average interval between eruptions has been gradually lengthening. In the 1950s, Old Faithful erupted roughly every 60 minutes. Now the average interval is closer to 90 minutes. The official explanation involves changes in the underground hydrothermal plumbing, shifts in the conduits and chambers that feed the geyser, that have altered the timing. But the deeper question is what caused those changes in the plumbing. And the answer, as it so often is at Yellowstone, points downward, into the heat, into the system that never stops. The hydrothermal system at Yellowstone is one of the most complex and largest on Earth. There are more than 10,000 geothermal features in the park: geysers, hot springs, mud pots, fumaroles, and no two behave exactly alike. Some are quiet and still, pools of water so clear and so blue that they look unreal, like something painted onto the landscape. Others are violent, boiling mud that churns and throws itself upward in thick, heavy splashes. Some steam constantly. Some are silent. Some make sounds that have no good analogy, a deep rhythmic knocking that comes from underground, or a high-pitched hissing that rises and falls without any pattern you can track. The Grand Prismatic Spring is one of the most photographed places in the park. Seen from the ground, it's impressive. A large, vivid pool surrounded by rings of orange and yellow and rust-colored material. But seen from above, it becomes something else entirely. The concentric rings of color, the result of different species of heat-loving microorganisms living at different temperature gradients, form a pattern that looks almost deliberate, almost designed. Pilots who have flown over it and researchers who have hiked to the overlook all describe the same initial reaction, that it doesn't look like something that should exist in nature, that it looks like something that was placed there. The organisms living in that spring, and in the hundreds of similar hydrothermal environments throughout the park, represent one of the most significant biological discoveries of the 20th century, and most people have never heard the full story. In 1966, a microbiologist named Thomas Brock began studying the bacteria living in the boiling springs of Yellowstone. The scientific consensus at the time held that life could not exist above certain temperature thresholds. It was assumed that the heat would destroy the cellular machinery that living things depend on. Brock found bacteria not just surviving in springs at temperatures approaching 70 or 80 degrees Celsius, he found them thriving. The organism he identified, Thermus aquaticus, changed biology. From it came an enzyme called Taq polymerase, which became essential to the polymerase chain reaction, or PCR, the technique used in DNA testing, criminal forensics, disease diagnosis, and virtually every corner of modern molecular biology. The virus tests that were administered by the billions during the pandemic relied on a process that could trace its origins to a bacterium discovered in a hot spring in a national park in Wyoming. What was living in those pools turned out to be not just surviving despite the heat. It was optimized for it. It had evolved to require the very conditions that were supposed to make life impossible. But the thermophiles and the heat-loving organisms are only one layer of the microbial world at Yellowstone. Below the visible springs, in the hydrothermal channels, and the cracks in the rock, and the deep sediment of Yellowstone Lake, there are communities of microorganisms that have never been fully catalogued. Researchers who have attempted to sample and sequence the microbial life in even a small area of the park consistently find species that have never been documented anywhere before. The park's thermal diversity, the sheer variety of temperatures, pH levels, chemical compositions, and oxygen concentrations across different features has created hundreds of distinct ecological niches, each one potentially harboring life that has evolved in complete isolation for thousands of years. Scientists estimate that the vast majority of species living in Yellowstone's hydrothermal features have not yet been identified. That's not a footnote. When researchers say that the majority of life in one of the most studied national parks in the world remains undescribed, they are saying something profound about the limits of our knowledge. Yellowstone has been formally studied for over 150 years, and we are still, in the most literal sense, just beginning to understand what's living in it. Every time someone goes in with new sampling equipment or better sequencing technology, the number of unknown organisms goes up, not down. The more carefully you look, the more is there. But the living things in the hydrothermal features are also what make those features genuinely dangerous. Not the microbes themselves, though some of the chemical processes they drive produce acids that can dissolve rock and metal. The danger comes from the pools. The water in the Grand Prismatic Spring reaches temperatures of around 87 degrees Celsius at the center, nearly boiling at Yellowstone's elevation. The springs are often extremely acidic or extremely alkaline, and the beauty of them, the clarity, the color, the stillness, creates a visual impression that can be fatally misleading. The most stunning things in the park are also, in many cases, the most lethal. In 1981, David Kerwin watched his dog jump into the Celestine pool near Fountain Paint Pot. The pool temperature was approximately 93 degrees Celsius. Kerwin jumped in to save the dog. He was pulled out by witnesses within seconds. He died the following morning. When a park emergency worker asked him immediately after being pulled from the water if he understood what he had done, Kerwin reportedly said, "That was a stupid thing I did." Those were among the last coherent words he spoke. The burns covered his body so thoroughly that when the helicopter crew went to transport him, his skin came away at the contact points. The dog did not survive either. That is not an isolated incident. Between 1890 and the mid-2010s, at least 22 people died after entering or falling into Yellowstone's thermal features. Many more were severely injured. The overwhelming majority of those deaths happened not because people wandered off into obscure wilderness, but because of small decisions, stepping slightly off a boardwalk to get a better photo, moving onto ground that looked stable but wasn't, crouching too close to the edge of a pool that didn't advertise its temperature. The hydrothermal crust in many parts of the park is dangerously thin. In some places it is only a few inches thick, suspended over water or mud at temperatures that would cause fatal injury within seconds of contact. The crust often looks solid. It looks like packed earth or dried mud. It can support the weight of a boot for a moment before it doesn't. The last recorded death from a thermal feature at Yellowstone happened in 2016. A man named Colin Scott, visiting from Portland, Oregon, left the boardwalk near the Norris Geyser Basin with his sister. They had been looking for a place to soak in geothermal water, a practice that is illegal everywhere in the park, but has a long informal history in certain areas. Scott slipped and fell into an acidic hot spring. A rescue attempt was made. By the following day, the acid and heat had dissolved his body almost completely. Recovery teams found essentially nothing. The sister filmed portions of what happened. The footage was seen by investigators and then suppressed. What it showed remains in the category of things that the people who viewed it don't describe in detail. That detail, the dissolution, is not sensationalism. It reflects something real about the chemistry of certain hydrothermal features at Yellowstone. Some of the most acidic springs in the park have pH levels below 2, comparable to battery acid. The combination of extreme heat and extreme acidity creates conditions in which organic material can be broken down at a rate that is deeply unsettling to think about. Rangers who work in the geyser basins know this. They also know that the geography of those features means that a person who falls in at the wrong angle in the wrong place may not be visible from the boardwalk within moments of entering the water. The steam alone can obscure a fall from bystanders standing just feet away. And yet people keep stepping off the boardwalks. It happens constantly, not the fatal incidents but the violations. Rangers intercept visitors who have stepped onto the thermal crust dozens of times per season. The visual pull of the features is real. Photography creates pressure to get closer. The pools and the steam and the colors do something to the part of the brain that evaluates risk, and the risk evaluation doesn't always win. There is something about Yellowstone's hydrothermal landscape that invites approach in a way that other, obviously dangerous environments, cliff edges, fast water, do not. Scientists who study risk perception have noted this, but haven't fully explained it. Part of the explanation might be the sounds. Hot springs don't roar, they don't crash or thunder. They lap and hiss and occasionally bubble with the kinds of sounds that a pot of soup makes when it's just starting to simmer. The auditory cues that humans associate with danger, loud, sudden, sharp, are mostly absent. What you get instead is something almost soothing. A low, steady sound. Heat you can feel, but that feels more like warmth than threat. Steam that smells of sulfur, which most visitors register as unpleasant but not alarming. The features announce themselves as strange and foreign, but not necessarily as something that could kill you in 10 seconds flat. That quality, the strangeness that doesn't read as danger, runs through the entire park. Yellowstone has a way of presenting things that are extraordinary, as though they are ordinary. You can drive along a road and watch bison standing 15 feet from your car window, enormous and motionless, and after a while it starts to feel unremarkable. You can watch a geyser erupt and realize that the eruption is both astonishing and somehow expected. The park normalizes the abnormal with an efficiency that is almost deceptive, and the things that look most normal, the flat meadows, the gentle thermal areas, the wide open basins, are often the places where the geology is most extreme. The Sour Creek Dome is one of two resurgent domes within the Yellowstone caldera. It's not a dramatic feature. It doesn't look like much if you don't know what you're looking at. It's a gentle uplift in the terrain, the kind of subtle rise that most visitors would drive past without a second thought. But the Sour Creek Dome has risen by more than 85 centimeters since 1923, when measurements began. In some years, the uplift has been measured at several centimeters per year. In other years, the ground has dropped. The movement is driven by the pressure and movement of magmatic fluids and gases far below, the deep engine working, adjusting, redistributing itself. The dome is, in effect, the skin of the system, and the system is not sleeping. There is an array of GPS sensors, seismometers, tilt meters, and continuous monitoring instruments distributed throughout the park that tracks this movement in real time. The Yellowstone Volcano Observatory, operated jointly by the USGS, the University of Utah, and the National Park Service, processes streams of data from hundreds of instruments. They detect thousands of earthquakes per year. Most are tiny, magnitude 0.5 or lower, imperceptible to anyone standing on the surface. But Yellowstone is one of the most seismically active regions in the United States. The earthquakes don't stop. They do, however, change. In 2017, the park experienced what seismologists called a swarm, a period of unusually elevated earthquake activity that lasted for several months. Over 2,400 earthquakes were recorded between June and September of that year, with the largest reaching a magnitude of 4.4. This was the longest and most intense earthquake swarm recorded at Yellowstone in decades. Buildings didn't fall. People didn't feel most of them. Life in the park continued normally, at least on the surface, but the scientific community was paying very close attention. Because earthquake swarms at Yellowstone are not like random seismic activity elsewhere. They are connected, sometimes directly, sometimes in ways that remain unclear, to the movement of fluids and gases deep in the hydrothermal and magmatic system. When magma moves, fluids move. When fluids move at pressure through rock, they cause tremors. When tremors cluster and repeat, it indicates that something in the underground plumbing is in a state of change. Most of the time, those changes are minor. Most of the time, the swarms subside and the system settles back toward equilibrium. But the monitoring continues because at Yellowstone, the history of what the system is capable of is written in the rock itself, and the rock remembers things that would take your breath away. The three major eruptions of the Yellowstone hotspot, 2.1 million years ago, 1.3 million years ago, and 640,000 years ago, were among the largest volcanic events in the history of the planet. The most recent of those three deposited ash across the entire western United States. The eruption 2.1 million years ago was even larger. It released enough material to bury the state of Texas under several feet of volcanic debris. These weren't eruptions in any conventional sense. They were planetary events, the kind of events that restructure climate, kill ecosystems across continents, and leave marks in the geological record that are visible 640,000 years later, if you know where to look. The rock strata in states as far away as Kansas contain a distinct pale layer from that eruption, a visible scar in the Earth's autobiography. And the system hasn't gone dormant. Hotspots don't go dormant. They move, or rather the continental plate above them moves, carrying the crust over the stationary heat source. The track of the Yellowstone hotspot across the North American plate can be traced backward through time in a chain of calderas and volcanic features stretching westward through Idaho, a path of ancient destruction that marks where the hotspot has been as the continent drifted above it. This is the same general process that created the Hawaiian Islands, but the Yellowstone hotspot sits beneath continental crust rather than oceanic crust, and continental crust is thicker, more complex, and interacts with rising magma in ways that produce more explosive results. What created Hawaii as a chain of tropical islands created Yellowstone as something harder to look at directly. The magma chamber, or chambers, because the research increasingly suggests there are multiple connected reservoirs at different depths, is not a molten lake sitting just below the surface waiting to burst. This is one of the most common misconceptions about Yellowstone. The magma system is more like a partially molten sponge, a vast body of hot rock that is somewhere between solid and liquid, with pockets of actual melt distributed throughout. The upper chamber sits roughly 5 to 10 kilometers below the surface. The lower chamber is deeper and larger. And below that, the mantle plume itself, the column of anomalously hot rock rising from deep in the earth, continues downward for hundreds of kilometers. The heat source is not local. It extends to the very roots of the planet. What the research suggests is that for a full eruption to occur, several conditions would need to be met simultaneously. The melt fraction in the magma body would need to increase significantly. Pressure would need to build to the point where the overlying rock could no longer contain it, and a triggering mechanism would need to initiate the actual rupture. None of those conditions currently exist at Yellowstone, and scientists emphasize this point clearly because the public narrative around the volcano has a tendency to skip over nuance. But the word currently carries weight. The system is not static. The conditions change. They have changed before. Slowly, imperceptibly to any individual lifetime, but with certainty over geological time. The 1959 Hebgen Lake earthquake is the event that most clearly illustrated what the region is capable of, even outside of a volcanic context. On August 17th, just before midnight, a magnitude 7.5 earthquake struck west of Yellowstone. It was one of the largest earthquakes in the continental United States in the 20th century. The shaking collapsed an entire mountainside into the Madison River Canyon in seconds, burying a campground beneath rock and debris. The landslide created a natural dam that formed what is now called Quake Lake. 28 people died. The earthquake was felt across 5 states. At Yellowstone itself, it changed the hydrothermal system dramatically. Geysers that had been dormant for years erupted, others went completely quiet, and new geothermal features appeared in the following days and weeks, in places where none had existed before. The underground plumbing rearranged itself overnight. The connection between seismic events and hydrothermal behavior at Yellowstone has been documented repeatedly, and what it reveals about the sensitivity of the system is striking. In 1992, a magnitude 7.3 earthquake struck Landers, California, more than 800 miles from Yellowstone. Within minutes, geysers at Yellowstone responded. The amplitude of the seismic waves passing through the park temporarily altered the pressure in underground water columns, and geysers began erupting more frequently in the hours following the distant quake. The same pattern was observed after the 2002 Denali earthquake in Alaska, and after the 2011 Tohoku earthquake in Japan. The shock waves traveled around the planet and reached Yellowstone's hydrothermal system, and the system felt them. It responded. That kind of sensitivity to events thousands of miles away says something about how finely balanced the pressure in that underground network is. The hydrothermal explosions are a good example of what an imbalanced system can do without any volcanic eruption at all. A hydrothermal explosion doesn't involve magma. It occurs when superheated water that is under pressure deep underground suddenly has that pressure reduced, perhaps by an earthquake shifting the rock above it, or by natural erosion exposing the water column, and flashes almost instantly to steam. The expansion is violent and immediate. The resulting explosion can be powerful enough to throw boulders the size of cars across a considerable distance. It looks, to anyone standing nearby, like an artillery strike emerging from the ground, except there's no warning. The most recent significant hydrothermal explosion at Yellowstone occurred in 1989 at a feature called Pork Chop Geyser. On September 5th of that year, Pork Chop, which had been a relatively predictable geyser, exploded. The explosion left a crater approximately 5 meters across and threw debris 50 meters in every direction. Fortunately, no one was standing near the feature when it happened. In the days before the explosion, rangers had noted that the geyser's behavior had changed. The intervals between eruptions had become irregular, and the force of each eruption had increased, but the explosion itself came without a final warning that anyone had time to act on. The feature simply ceased being what it had been and became something else. Pork Chop was a small event by historical standards. Mary Bay on the northern shore of Yellowstone Lake contains a crater that is approximately 2.6 kilometers across. That crater was formed by a hydrothermal explosion roughly 13,800 years ago, an explosion so large that it would be classified as catastrophic by any modern standard. The force required to excavate that crater from solid ground was enormous. Researchers who have mapped the subsurface of the Mary Bay area have found evidence of multiple overlapping craters from separate events, suggesting that hydrothermal explosions have occurred in that location repeatedly over thousands of years. The conditions that created those events, superheated water under pressure, fault lines, volcanic heat, are all still present. Nothing about that location has fundamentally changed. Yellowstone Lake itself is one of the stranger features of the park, large, cold-looking, sitting at an elevation of over 7,700 feet and utterly deceptive in what lies beneath its surface. The lake floor is geologically some of the most complex terrain in the park. There are active hydrothermal vents on the lake bottom. There are areas where the sediment is measurably, significantly hot. There are massive bulges on the lake floor, called inflated plain features, that have risen and subsided over time in patterns consistent with pressure changes in the underlying hydrothermal system. And there are zones where the lake water above the thermal features is anomalously warm, creating temperature inversions that affect the behavior of fish and dissolved oxygen levels in ways that researchers are still working to fully characterize. Divers who have gone into Yellowstone Lake describe it as one of the most disorienting underwater environments they have encountered. The visibility varies dramatically. In some areas, the water is exceptionally clear. In others, thermal plumes rising from the bottom create convection currents that distort everything, making it difficult to maintain orientation or judge distance. The hydrothermal vents emit gases, and some areas of the bottom produce a shimmering visual effect, heat hazes underwater, that researchers say is unlike anything they've seen elsewhere. The bottom of Yellowstone Lake is one of the least surveyed environments in the park, largely because the conditions make survey work difficult, and the temperature at certain depths, near the vents, makes standard diving equipment unreliable. In the late 1990s, researchers conducting sonar mapping of the lake floor discovered a series of underwater features that were considerably larger and structurally more significant than expected. Among them were domed formations, bulging uplifts of the lake bed, that matched the kind of pressure-driven deformation associated with hydrothermal activity over a magmatic system. One of these features, in the southern portion of the lake, had dimensions suggesting a large-scale process operating beneath it. The research suggested that the lake floor was not a passive surface sitting above a volcanic system. It was part of the system. It was being shaped and deformed by the same forces that shaped the geyser basins above ground. When scientists began looking more carefully at the behavior of the lake over long time periods, they found something else. The lake tilts. Not perceptibly, not in a way you would notice standing on the shore. But using precise measurement, it's clear that the lake surface is not level in any fixed way. As the ground on the northern side of the lake uplifts and the southern side subsides, driven by the pressure dynamics of the underlying magma and hydrothermal system, the lake water redistributes itself. Over the past century, the southern shore has lost land as the lake level above that shoreline has risen, while the northern shore has gained land. The lake is slowly pouring itself from one end toward the other. The ground it sits on is not still. It is not still in any moment that we have been able to measure. There are things in the park that the geology records but human observers missed entirely. Events that left physical traces but happened before anyone was watching. One of the most striking is the scale of the catastrophic flooding that occurred at the end of the last ice age, when glaciers covering Yellowstone melted, and meltwater, combined with the collapse of glacial ice dams, sent enormous volumes of water rushing through the valleys. The Snake River Plain to the south of Yellowstone bears the marks of that flooding. Channels carved into rock, boulders moved miles from their origin points, sediment deposits that tell the story of water moving at speeds and volumes that have not been seen since. The rivers in the region today are the quiet descendants of events that would have been terrifying to stand next to. The modern park, even without any catastrophic event, has seasons of weather that are extreme by any standard. Winter temperatures at Yellowstone can fall below -40 degrees Fahrenheit and do so regularly. The high elevation, most of the park sits above 7,000 feet, means that snowfall accumulates to depths that make overland travel without specialized equipment essentially impossible. Roads close. The park becomes something else entirely. A place of silence and whiteness and cold so thorough that it changes how everything sounds. Rangers who stay through winter describe the experience of being in an environment that most humans will never see. The geysers steaming against -30-degree air, the silence of the snow-covered forest, the occasional distant sound of ice moving on the lake. And beneath all of it, unchanged and unaware of the season above, the pulse of the heat below. That contrast, the killing cold above and the volcanic heat below, is one of the defining characteristics of the park in winter. Bison survive Yellowstone's winters by using the thermal areas as refuges. The ground around hot springs and geothermal vents melts snow and keeps soil temperatures above freezing, creating patches of accessible vegetation when everything else is buried under feet of white. Bison have learned, over generations, over centuries of selection, where those patches are. They move to them in winter with a precision that looks almost planned. Wolf packs follow the bison. The thermal areas become the centers of wildlife activity in the coldest months, gathering points organized not around water or shelter in the usual sense, but around underground heat. Wolves were reintroduced to Yellowstone in 1995, after an absence of roughly 70 years. Their return is one of the most studied wildlife reintroductions in the history of conservation, and what the research revealed over the following decades was more complex than anyone initially predicted. The wolves didn't just reduce elk populations, as expected. They changed elk behavior. Elk that had previously grazed freely along riverbanks became more cautious, spending less time in open areas where wolves could approach from multiple directions. With less elk grazing pressure, willows and aspens and other vegetation began to recover along stream banks. The roots of that recovered vegetation stabilized stream banks. Stream channel dynamics changed. Fish populations responded to changes in water temperature and habitat structure. The return of the wolves was felt through the entire ecosystem, all the way down to the behavior of rivers. The ecologists who tracked this called it a trophic cascade. But what the textbook summary of that story doesn't always mention is that the cascade was not clean or simple. The wolf reintroduction generated intense conflict. Ranchers outside the park boundaries lost livestock. Political battles over wolf management stretched on for years and continue in some form today. The wolves themselves didn't behave exactly as models predicted. Some packs moved out of the park. Some elk populations recovered faster than expected in certain areas, slower in others. The ecosystem is not a machine with predictable outputs. It is a living system that responds to change in ways that surprise even the researchers who know it best. The surprises are not mistakes in the model, they are the system being itself. Bears present a similar complexity. Yellowstone is home to both black bears and grizzly bears, and the grizzly population in the greater Yellowstone ecosystem has been one of the most closely monitored wildlife populations in North America for decades. Grizzly numbers have recovered significantly since the low points of the 1970s, when fewer than 150 individuals were estimated. Current estimates suggest somewhere between 700 and 1,000 grizzlies in the broader ecosystem. The recovery has been called a conservation success story, and in many ways it is. But the grizzlies of Yellowstone are also changing in ways that the success narrative doesn't fully capture. Their diet has shifted. One of the historically most important food sources, whitebark pine seeds, which grizzlies depend on in late summer and fall to accumulate the fat reserves they need before hibernation, has been declining because whitebark pines across the West are dying at high rates. A combination of mountain pine beetle infestations and a fungal disease called white pine blister rust is removing these trees from the landscape faster than they can regenerate. Grizzlies that can't find whitebark pine seeds have to compensate by seeking other food. Some have shifted their ranges to find alternatives at lower elevations. Some have come into increased conflict with humans and livestock as a result. The animals are adapting, as they always have. But the pace of change in their food web is faster than it has been in living memory. There is also the matter of the grizzly's relationship with the thermal features. Researchers who study movement patterns in the bear population have noted that grizzlies, particularly in spring when they emerge from hibernation, tend to move through geothermal areas with a kind of deliberate familiarity. They know where the features are. They know where the thermal ground is warm enough to make digging easier, or where early plant growth is accelerated by underground heat. Individual bears have been observed returning to the same thermal locations year after year, at the same time of year, with a consistency that suggests learned behavior passed down through generations. The park's thermal features are not just geological curiosities to the wildlife. They are resources. They are part of the animal's cognitive map of a landscape they have lived in for far longer than we have been studying them. There are other, less studied behaviors that have drawn the attention of wildlife researchers. Ravens, which are abundant at Yellowstone and among the most behaviorally complex birds on Earth, have been observed gathering around geothermal features in numbers that seem disproportionate to any obvious food source. The congregations are not always easily explained. Ravens are attracted to bison carcasses and wolf kills, which they can smell from great distances and which are common enough in the park. But some of the gatherings near thermal features occur in the absence of any obvious carrion. Researchers studying raven cognition have suggested that ravens may be using thermal updrafts from geothermal features for thermoregulation or navigation. Others have been more cautious, noting that the behavior may have explanations that the current observation record isn't yet detailed enough to reveal. Whatever the reason, the birds keep returning to the same features in the same seasons, with a consistency that demands some explanation. The landscape changes from year to year in ways that are more than seasonal. New features appear, old ones shift or go dormant. In 2018, a hydrothermal feature near Biscuit Basin called Ear Spring erupted unexpectedly, throwing water and debris several feet into the air, along with a collection of objects that had been deposited in the spring over decades. Among the debris, coins, cigarette butts, old straws, a concrete block, and a handkerchief from the 1930s. The spring had not erupted noticeably in decades. What was inside it represented accidental archaeology, a record of human presence at the feature going back more than 70 years. Everything that visitors had tossed in, or that had been washed in, or had simply blown in by wind over the years, had been sitting at the bottom, accumulating. And then one day the spring decided to send it all back. The Ear Spring eruption illustrated something that is easy to intellectually know but harder to actually feel. The thermal features at Yellowstone have their own deep time. They operate on schedules and in response to pressures that exist on scales where human lifetimes are barely measurable. A spring that has been quiet for decades is not asleep. It is waiting for conditions to shift, and when they shift, there may or may not be any visible warning. The spring doesn't slow down and give you a look. It doesn't send a signal. It just changes, And if you happen to be standing in the wrong place when it does, the relevant information arrives very quickly. That same principle applies across the entire park. The Norris Geyser Basin, located in the northwest section of the caldera and considered the most thermally active area in the park, undergoes periodic episodes that scientists call thermal disturbance events. These were first clearly documented in the mid-1980s, but have likely been occurring for far longer. During a thermal disturbance event, the basin's hydrothermal behavior changes over the course of days. Features that were quiet become active. Boiling spreads to new areas. Water that had been clear turns milky and turbid from minerals being released from the walls of underground channels. New fumaroles open in places that had previously been stable ground. The boardwalks, which are routinely moved and repositioned in the Norris Basin because the active ground makes fixed structures impractical, sometimes need emergency repositioning. The most dramatic thermal disturbance in recorded history at Norris occurred in 2003. Ground temperatures in parts of the basin rose so sharply that the soil itself became hot enough to cause concern about visitor safety. Areas that had been accessible for decades were closed. Trees in certain zones died within weeks as the ground temperature around their root systems crossed lethal thresholds. Boardwalks buckled. The hydrothermal features in the basin reorganized themselves with a speed that was jarring to anyone who had been watching the area over years. The event lasted for months and left the basin looking distinctly different from how it had appeared before. Researchers who had spent years studying Norris said the experience of watching that change happen was unlike anything they had previously encountered in the field. What caused the 2003 disturbance has been debated. The most widely accepted explanation involves a temporary blockage of the hydrothermal system at depth, a buildup of silica or mineral deposits sealing off a pathway, which then shifted or ruptured and released backed up heat and fluid to the surface with unusual force. But researchers working with the data from that event have noted that simple blockage and release doesn't fully account for all the spatial patterns of where the disturbance was strongest and where it was absent. There may have been a deeper driver, something in the magmatic or hydrothermal system at depth that the surface-level interpretation doesn't fully reach. The data points toward an explanation without quite delivering one. A similar, though less severe, disturbance occurred in 2015, and again the spatial patterns raised questions. The relationship between the upper hydrothermal system, the geysers and springs and fumaroles visible at the surface, and the deep magmatic and hydrothermal system below is not a simple top-down relationship where everything at the surface is a direct expression of what's happening below. The system has intermediate layers that buffer and alter and store. Fluids mix, gases interact. Pressure gradients form and dissolve over timescales that don't correspond to any season or any year. What you see at the surface is more like the last step in a long chain of causation than a direct window into the source. Some of the most evocative descriptions of Yellowstone's deep character come not from scientists, but from the people who have spent the most uninterrupted time in the park, under conditions that make observation more intense. Night in the backcountry of Yellowstone is a different experience from night in almost any other landscape. The altitude and the distance from any city means that light pollution is nearly absent. On clear nights, the star field above the park is extraordinary, dense and bright in a way that people who have grown up near cities sometimes find disorienting, because the sky looks different. It looks deeper. The Milky Way is visible as a structural feature of the night sky, not just a name. And from certain high vantage points, the geothermal steam rising from the geyser basins catches the moonlight, so that below you there are pale columns of vapor rising into the darkness. And above you the full density of the night sky, and somewhere between them you are standing on ground that is warm in places where it shouldn't be. The sounds of the park at night are another thing entirely. Wolves howl, but not as often as stories suggest, and the sound carries differently than expected, flattened and shaped by terrain in ways that make it hard to locate the source. Elk bugle in autumn with a sound that has no close human parallel, a high-pitched rising call that ends in a series of grunts, unnervingly loud from close range. Geysers erupt, and you can hear them from surprising distances in still night air, a rushing, forceful sound like water being pushed very fast through a narrow space, And then there are sounds that are harder to categorize, a low resonance that seems to come from everywhere and nowhere. A deep, slow vibration that your body registers before your ears do. Rangers describe this as the sound of the ground thinking, which is not a scientific description, but it's not wrong either. The Yellowstone River at night, particularly in the canyon reaches below the lower falls, generates a sound environment that is almost overwhelming. The water drops 308 feet at the lower falls, one of the largest waterfalls by volume in the western United States. And the sound it produces in the canyon below is not just loud but layered and complex. It fills the canyon so completely that you can't hear anything over it. The canyon itself, with walls of yellow and orange and pink rhyolite stained by hydrothermal fluids that gave the park its name, amplifies and reflects the sound in ways that create strange resonances. At night, with only starlight and spray and the slight vibration of the footbridge near the canyon rim, the falls are one of those places that alters something in the way you experience space. You stop having a normal sense of scale. Everything becomes either very small or very large, and you can't quite tell which one you are. The canyon itself is a consequence of hydrothermal activity in a way that isn't immediately obvious. The beautiful colors of the canyon walls, the yellows and oranges and chalky whites, are the product of hydrothermal alteration of the rhyolite rock. Acidic hydrothermal fluids, moving through fractures in the rock over thousands of years, have altered the mineralogy of the canyon walls, converting the rhyolite into a softer, more erodible material. The Yellowstone River, cutting through this weakened material, was able to carve the canyon far more quickly than it would have been able to cut through unaltered rock. The canyon exists because the ground it's cut into was already chemically weakened by the same processes that created the springs and geysers. The landscape is a consequence of the heat, even where the heat isn't visible, even where it looks like it should have nothing to do with volcanoes. That same principle extends to the geomorphology of the entire park. The gentle topography of the caldera interior, the basins, the thermal flats. All of it has been shaped by a history of volcanic activity and hydrothermal alteration that makes Yellowstone's landscape unlike anything formed by normal erosion alone. The soil chemistry in the thermal areas is unique. The vegetation patterns follow the underground thermal contours in ways that are invisible from the surface but legible in aerial photography if you know the signatures. The trees grow in patterns that reflect what's happening far below them. The rivers run where they do, partly because the underlying thermal structure directed the erosion over thousands of years. Everything is connected to the heat. It influences things at the surface that give no visible sign of that connection. Human history at Yellowstone is older than the European exploration narrative usually acknowledges. Native American peoples lived in and around the Yellowstone region for at least 11,000 years. Some archaeological evidence suggests human presence going back further. The obsidian found in Yellowstone, formed from volcanic activity and unusually pure and workable, was traded across enormous distances. Obsidian point artifacts from Yellowstone have been found at archaeological sites in Ohio and other eastern states, suggesting trade networks that stretched across the continent. The people who used those trade routes knew this landscape intimately, in ways that are only partially recoverable from the archaeological record and not at all recoverable from the oral tradition if you don't already know what you're looking for. The Crow people called the thermal features evil water. The Shoshone used certain hot springs for food preparation and bathing, carefully and with a knowledge of which features were safe to approach and which were not. The Blackfeet and the Bannock and others who traveled through the region all had relationships with the geothermal landscape that were practical and specific, knowledge built over generations about the behavior of features that European explorers would later approach as curiosities or novelties. When John Coulter became the first non-Native American recorded to have traveled through the region, around 1807, after splitting off from the Lewis and Clark expedition, he returned with descriptions that his contemporaries found so implausible that the region was sarcastically nicknamed Coulter's Hell. The geysers and boiling pools and sulfurous steam that Coulter described didn't fit into the conceptual world of his audience. They assumed exaggeration. The truth, as it turned out, was considerably stranger than what he had actually described. The reports that eventually compelled official exploration of the region came decades later. The Washburn-Langford-Doane expedition of 1870 produced accounts that were widely circulated and began to build public interest in protecting the region. 2 years later, in 1872, Yellowstone became the world's first national park, established by an act of Congress under President Ulysses Grant, decades before the concept of national parks had become an established framework anywhere in the world. The decision to protect the region was motivated by a mixture of genuine appreciation for its natural wonders and a desire to prevent private commercial development of the features, which some early visitors had already attempted to exploit. One entrepreneur had begun charging admission to view certain geysers. Others had collected and removed significant quantities of geyserite and mineral deposits. The park was created partly to prevent the wonder from being sold. The early history of the park is full of incidents and misadventures that reflect both the genuine danger of the environment and the sheer novelty of what park managers were dealing with. The first tourists who came to Yellowstone in any significant number arrived in the 1880s, with the completion of a rail line to the park's edge. They were almost entirely unprepared for what they found. People fell through thermal crusts. People were burned by springs. A series of incidents involving tourists attempting to launder handkerchiefs and clothing in geyser pools, whose underground plumbing is not improved by soap, contributed to changes in the eruption behavior of several features. The underground plumbing of geysers is exquisitely sensitive to what is introduced into it. Some features altered by those early interventions have never fully recovered. Early managers of the park also discovered that the scale of the place made enforcement of any rules essentially impossible for decades. The park is 2.2 million acres. In the first years of its existence, the administrative staff consisted of a superintendent and a small number of assistants, with essentially no enforcement authority and no funding for infrastructure. Poaching was endemic. Thermal features were damaged. The army was eventually called in to manage the park, a period that lasted from 1886 to 1918, when the newly created National Park Service took over. And even with military resources, controlling what happened across 2.2 million acres of difficult terrain was a near impossible task. The park was simply too large, too remote, and too full of things that people wanted to interact with, exploit, or take home. The management of the park today is enormously more sophisticated. The monitoring network, the research programs, the ranger staff, the visitor management infrastructure, all of it represents a system designed to both protect the park and communicate its nature to the millions of people who visit each year. About 4 million people visit Yellowstone annually. On a peak summer day, the parking lots at the major geyser basins fill to capacity by mid-morning, and traffic on the Figure 8 road system through the park can slow to a crawl behind a bison herd that has decided to walk down the center of the road. The bison don't slow down for people. They never have. They were here before the roads existed, and their movement patterns predate every paved surface in the park by thousands of years. The roads through Yellowstone pass directly over the caldera. The boardwalks in the geyser basins are built on top of one of the most thermally active surfaces on Earth. The visitor center at Old Faithful sits in a location that, in the event of a significant hydrothermal explosion or surface deformation event, would be directly affected. The campgrounds, the lodges, the stores, all of it occupies space within the caldera or in the immediate vicinity of it. This is not a critique of the park's management. It is simply the nature of the situation. You cannot have Yellowstone as a destination and simultaneously keep people at a safe distance from everything that makes Yellowstone what it is. The two realities are inseparable. The wonder and the risk come from exactly the same source. Scientists who study the system have been clear about what the realistic risk profile looks like. A full caldera-forming eruption at Yellowstone in any near-term geological period is considered unlikely, but not impossible. The probability in any given year is often cited as approximately 1 in 730,000. That sounds small. For context, the probability of being struck by lightning in the United States in a given year is approximately 1 in 1,000,000. So the Yellowstone probability is actually higher than the lightning probability. Whether that framing is reassuring or alarming depends on what you do with the comparison. Lightning kills dozens of Americans every year. What scientists are more immediately focused on, because the probability is far higher and the consequences would still be severe, is the possibility of a large hydrothermal explosion. Mary Bay scale events, not as large as the explosion that formed that crater 13,800 years ago, but still powerful enough to be catastrophic within the immediate area of the park and to affect atmospheric conditions across a wider region, are considered possible within much shorter time frames than a caldera-forming eruption. The monitoring network is designed to detect precursors, but the challenge is that the precursors for a hydrothermal explosion can be subtle and brief, and the speed of the events themselves, from initial signs of increased activity to the actual explosion, can be very short. Short enough that even a working warning system might not provide usable lead time. The gas emissions are worth spending a moment with, because they represent a largely invisible but significant hazard that gets less attention than the more dramatic features. Yellowstone releases somewhere between 45,000 and 60,000 metric tons of carbon dioxide per day through its hydrothermal system. This is not CO2 from any industrial activity or human source. It is volcanic CO2 rising from the magmatic system below. It disperses into the atmosphere and causes no harm at normal concentrations. But in certain topographic situations, low-lying areas, hollows in the terrain, closed valleys, volcanic CO2 can pool in concentrations high enough to be lethal. CO2 is heavier than air. It settles near the ground. Animals that pass through areas of CO2 accumulation can be asphyxiated before the symptoms of oxygen deprivation register as unusual. This has happened at Yellowstone. Not dramatically, not with any single large event, but there are documented cases of animals dying in areas near geothermal vents in patterns consistent with CO2 exposure. The gas is colorless and odorless and, in concentrations that are merely uncomfortable rather than lethal, produces symptoms: headache, drowsiness, confusion, that can feel like other causes and may not be immediately identified as gas-related. A person sitting in a low-lying area near an active vent, who begins to feel tired, might attribute the sensation to the altitude or the heat or the exertion of the walk. The gas would not advertise itself, and the tiredness would not necessarily stop increasing. Hydrogen sulfide presents a different profile. It is detectable by smell at very low concentrations, the characteristic rotten egg smell that visitors notice throughout the geyser basins. This is actually a safety feature of a strange kind. The odor warns of its presence at concentrations far below those that would cause harm. But hydrogen sulfide causes olfactory fatigue. You stop smelling it after a short exposure, and at higher concentrations, it acts extremely quickly on the respiratory and nervous system. At high enough concentrations, it causes immediate unconsciousness. Workers in industrial settings where H2S is a hazard are trained extensively on this property. There is no gradual worsening that gives you time to respond. There is smell and then there is not smell, and if you are still in the presence of the gas at that point, the next thing is not necessarily anything at all. The Mud Volcano area, located in the eastern caldera region south of Hayden Valley, is one of the most intensely active hydrothermal areas in the park, with a concentration of boiling mud pots, acidic hot springs, and vigorous fumaroles that have been dramatically active since at least the earliest park records. The area smells overwhelmingly of sulfur. The ground is stained black and orange by iron sulfide deposits. The mud pots, pools of acidic, boiling mud, churn and splatter with a sound and consistency that evokes something industrial rather than natural. Trees near the most active features are dead, their bark chemically stripped, their roots cooked by the ground heat. The Mud Volcano area looks more than anywhere else in the park like what people imagine a volcanic landscape to be, like what a planet would look like if it were not yet finished. In the 1870s, the Mud Volcano itself was described by early visitors as a violent feature that erupted mud several feet into the air. By the time systematic photography of the park began in the late 19th century, the Mud Volcano had declined significantly. By the mid-20th century, it was much quieter. Then, beginning in the 1970s and accelerating through the 1980s and 1990s, the entire Mud Volcano area underwent a period of dramatic intensification. Temperatures in the soil rose. New features appeared. Existing features enlarged and became more violent. The area has continued to evolve. What it does today is not what it was doing 50 years ago. And what it was doing 50 years ago was not what it was doing 150 years ago. The features are not static monuments. They are processes. They are ongoing events that we happen to observe during one brief window of their long history. Dragon's Mouth Spring, just steps from the mud volcano, is one of the most sonically extraordinary features in the park. It is a hot spring that occupies a subterranean cave so that the boiling water is partially enclosed rather than open to the sky. The result is that the steam and the water and the gases inside the cave create pressure variations that produce a rhythmic slapping, whooshing, thudding sound, irregular enough to resist prediction, regular enough to seem patterned. The sound echoes from the cave walls and emerges from the opening in a way that is simultaneously unsettling and mesmerizing. The name was given by early park visitors who found the combination of the sound, the steam, the orange-stained cave walls, and the hot water slapping against the cave roof sufficiently evocative to suggest a living creature. Standing near it, you understand the impulse. Something in there sounds like it's breathing, it sounds like it's waiting for something. There is a stretch of the backcountry in the northwest of the park, the area around the Bekla River and the Falls River Basin, that is so remote and so seldom visited that it represents what Yellowstone might have been like before any management infrastructure existed. The Bekla region has the highest density of waterfalls in the park, dozens of cascades ranging from small drops to major falls that rival anything in the more accessible parts of the park in scale and beauty. The thermal activity in the Bekla is less dramatic than in the Norris or Old Faithful areas, but it's present. Warm streams mix with cold ones. Meadows that should be frost-covered in early spring are still green because of geothermal warmth percolating up from below. The landscape has a quality that is hard to name, a combination of wildness and warmth that feels like a contradiction until you understand what's underneath. Hikers who make it to the Bekla, and it requires a permit, significant planning, and a willingness to ford rivers that can be dangerously high in early season, consistently describe it as one of the most isolated and immersive experiences available in the American wilderness. The solitude is real. You can go days without seeing another person. The wildlife is abundant in the way that wildlife is abundant when it hasn't learned to be particularly cautious around humans. Bears in the Bekla are not accustomed to being photographed from boardwalks. They are going about their actual business, in their actual landscape, and the experience of encountering one at close range in that context is a different order of experience from an encounter in the developed areas of the park. It is the reminder that you are not, in that moment, the most significant presence in the landscape. Yellowstone Lake contains cutthroat trout that have inhabited the lake for thousands of years, isolated from other trout populations by the park's geography and elevation. The cutthroats are a keystone species. They feed grizzly bears, ospreys, otters, ravens, and a variety of other predators. But the cutthroat population has been severely impacted by the illegal introduction of lake trout, discovered in the early 1990s and requiring an ongoing and expensive management effort to control. The lake trout are larger and faster growing than cutthroats and occupy a slightly deeper part of the water column where bears and birds can't access them, meaning that every established lake trout represents a caloric resource that has been effectively removed from the surface predator community. The trout introduction has rippled through the food web in ways that continue to be measured. The story of the lake trout is a reminder that Yellowstone, for all its remoteness and protection, exists in a world that does not stop at its boundaries. Invasive species arrive accidentally, on fishing gear, on boat hulls. Air quality in the park is affected by pollution from far outside its borders. The climate warming that is shifting species ranges and altering precipitation patterns across the western United States is happening to Yellowstone too. The snowpack on the mountains that feed the park's rivers is declining. Fire seasons are getting longer and more severe. The whitebark pines are dying. These are not hypothetical future scenarios. They are ongoing changes that the people who work in and study the park can measure and observe from season to season. The park is not isolated from the world. The world is happening to it continuously. The fires of 1988 remain the defining catastrophic event in the park's modern management history. In the summer of that year, a combination of severe drought conditions, accumulated decades of fire suppression, and an unusual pattern of summer lightning ignitions produced a fire season of unprecedented scale. By the end of the summer, approximately 1.2 million acres, roughly a third of the park, had burned. The fires burned hot and fast through lodgepole pine forests that had built up a thick accumulation of dead material over decades. The summer was the driest on record. Attempts to suppress the fires with all available resources failed. The fires burned until autumn rains and snow finally suppressed them. At the peak of the fire season, the smoke from Yellowstone was visible from satellites as a dense plume, stretching hundreds of miles to the east. The aftermath of the 1988 fires was not the ecological catastrophe that some coverage suggested at the time. Yellowstone's fire ecology, the relationship between the ecosystem and periodic fire, was already well understood by ecologists who had studied lodgepole pine forests. Lodgepole pine cones are serotinous, sealed with a resin that melts only in the heat of a fire, releasing seeds onto a newly prepared seedbed. Fire is not a destroyer in lodgepole pine ecology, it is a mechanism. The fire clears the old stand, prepares the mineral soil, and releases the stored seeds all at once. Within a year of the 1988 fires, vegetation recovery was visible across large areas of burned terrain. The landscape that visitors see today, where burns are visible as standing dead trees with young forest growing beneath, is not a wound. It is a stage in a cycle that has been running for as long as lodgepole pines have existed. But the fire history of Yellowstone goes back much further than 1988, and the longer record tells a more complex story. Researchers who have drilled lake sediment cores from lakes within the park have been able to reconstruct the fire history of the surrounding area going back thousands of years by examining the layers of charcoal deposited in the sediment. The pattern they find is one of periodic large fire events separated by long intervals of relative fire absence. The 1988 event fits within that natural pattern. What is less certain is how the current climate trajectory, the ongoing warming and drying, will interact with the fire cycle. The intervals between large fire events may be shortening. The conditions that produced 1988 may become more common, and the young forests recovering from 1988 will themselves become the fuel source for the next large fire event whenever the conditions align for it. The cycle doesn't stop, it just waits. Deep below all of this, below the fires and the floods and the bison migrations and the hydrothermal features, the magmatic system continues on its own timescale, indifferent to the seasons and cycles that define life at the surface. The seismic tomography, the technique of using earthquake waves to image the interior of the Earth, the way a medical ultrasound images the interior of the body, has produced increasingly detailed pictures of the magmatic system over the past 2 decades. The picture that has emerged is more complex than early models suggested, and each refinement of the model tends to reveal a deeper layer of complexity rather than resolving to a simple picture. There are 2 distinct magma reservoirs. The upper one, closer to the surface, is a relatively shallow body of silica-rich magma. Below it, at considerably greater depth, is a larger body of basaltic magma, the deeper, hotter, less viscous material that represents the direct expression of the mantle plume. The 2 reservoirs are connected, but not in a simple vertical pipe. The connection is more complex and more interesting than that. The basaltic magma at depth heats and mobilizes the silica-rich magma above it, contributing heat and gases that rise through the system. The interaction between the 2 reservoirs, different in composition, different in temperature, different in viscosity, is part of what makes the Yellowstone system so complex to model and so resistant to the kind of simple prediction that would make everyone feel more comfortable. What would actually happen if the Yellowstone caldera were to erupt is a question that has generated enormous popular interest and some significant misrepresentation. The most dramatic versions, the extinction-level event, the immediate death of everyone within hundreds of miles, the end of civilization as depicted in a series of films and TV specials, are not the scenarios that scientists consider most likely, even in a worst-case eruption scenario. What would happen would be terrible enough without exaggeration. A full caldera-forming eruption would likely begin with a period of precursory activity, increasing seismicity, rapid ground deformation, significant changes in the hydrothermal system that would, with the current monitoring infrastructure, be detectable weeks to months in advance. It is not a scenario in which no warning would be available. The instruments are good enough that the approach of such an event would not be invisible. The eruption itself, in the most extreme models, would release enormous volumes of pyroclastic material, superheated gas and rock fragments expelled at high velocity. The immediate area of the park would be obliterated. Ash fall downwind would be significant across much of the continental United States. Prevailing westerly winds would carry the plume eastward. Areas downwind within several hundred miles would receive ashfalls measured in feet. The impact on agriculture, infrastructure, and air travel across the country would be severe and lasting. Climate effects, a volcanic winter caused by sulfur dioxide injected into the stratosphere, would be global and could persist for years. It would be, unambiguously, the worst natural disaster in the history of the United States by many orders of magnitude. But the modeling also makes clear that this is the most extreme end of the range. A smaller eruption, more comparable to the effusive basaltic lava flows that have occurred in the Yellowstone system between the three major caldera-forming events, would be far less catastrophic. The magmatic system is capable of erupting in more than one way, and the most probable near-term eruption scenario, if one were to occur, would not necessarily be the caldera-forming catastrophe of popular imagination. This distinction matters, because the way the system is often presented as a binary choice between complete normalcy and complete extinction misrepresents the reality of a complex volcanic system with a range of possible behaviors, most of which fall somewhere between those extremes. The researchers who spend their careers studying Yellowstone tend to have a relationship with the uncertainty that is different from either the dismissive or the catastrophist versions that circulate in popular media. They live with the incompleteness of the data. They build models that they know are approximations. They monitor a system that they understand better every year and yet continue to find surprising. Several of them have described the work as addictive precisely because of the uncertainty, because the questions keep opening into deeper questions, and because the system always has something that doesn't quite fit the current model. The career of studying Yellowstone is not a career of resolving questions. It is a career of refining the questions into sharper, more useful forms. One example of this is the infrasound research. Infrasound, sound at frequencies below the human hearing threshold, is emitted by geysers, by volcanic systems, by large hydrothermal features. Instruments designed to detect infrasound have been deployed at Yellowstone and have recorded a continuous low-frequency signal from the ground that is not fully accounted for by any individual identifiable source. It appears to come from the ground itself, from the hydrothermal system in aggregate, as though the entire basin is generating a persistent hum that lies just below the range where humans can consciously hear it. The researchers who have been working with this data describe it carefully and avoid dramatic interpretations, but they acknowledge that the signal is real, is consistent, and is not yet fully explained. There is also the matter of how animals respond to the infrasound environment. Studies of animal behavior in areas of high infrasound activity in other volcanic systems have suggested that some species can detect and respond to infrasound at frequencies and intensities below what human instruments can easily measure. If the ground at Yellowstone is generating a continuous low-frequency signal, one that has likely been essentially constant for thousands of years, then the animals that live in and around the park have evolved in that acoustic environment. They may be sensitive to changes in it in ways that we haven't measured, because no one was looking for that specific signal. This is the outer edge of what is known, and the outer edge is much wider than the center. There is a thermal feature in the backcountry of the park, not on any tourist map, not accessible by boardwalk, and intentionally kept vague in the scientific literature because of the fragility of the site and the risk of uncontrolled visitation. It is a hot spring, but unlike the open pools in the developed geyser basins, this one is partially enclosed by a rock formation that creates a kind of natural chamber around it. The water inside is very hot and very clear. The walls of the chamber are covered with microbial mats in colors and patterns that are extraordinary even by the standards of Yellowstone's thermal features. The colors shift depending on the angle of the light. The steam inside the chamber catches the light in ways that make it difficult to judge the dimensions of the space. There is no good photograph of it because the camera can't capture what it feels like to stand in front of it. Researchers who have visited this feature describe an experience of the place that is difficult to fully articulate in scientific language. The sound inside the chamber, the combination of the spring itself and the acoustics of the enclosure, is unlike anything they've encountered elsewhere in the park. Not threatening, not alarming, just deeply, fundamentally strange. One researcher described sitting near the entrance for a long time, not because there was additional data to collect, but because leaving felt like interrupting something. She said she knew intellectually exactly what she was looking at, a hydrothermal feature, a biological community, a geological formation. She knew what every element was, and still it felt like more than the sum of what she could name. She said she has thought about it almost every day since. That experience, the sense that Yellowstone contains something that exceeds what you can fit into existing categories, is not unique to scientists. Visitors who have spent extended time in the park, particularly in the less visited areas, return with it frequently. The park's physical extremity, the heat, the cold, the scale, the noise of the water, and the silence of the backcountry, and the steam and the darkness, combines to produce an experience that changes how you hold the world for a while afterward. Not because anything supernatural has happened, but because you have been in the presence of something that is genuinely, undeniably operating on a different scale than ordinary experience. And that difference in scale does something. It leaves a mark. The people who have worked at the park for the longest, the rangers who have spent decades in it, the researchers who have returned year after year, the maintenance workers and lodge staff who have lived inside its boundaries through full winters, they are not, by and large, people who speak in dramatic terms about what the park is. They tend toward the understated. They tend toward precision. They say things like it's complicated, and we don't fully understand that yet, and it's not what most people expect. They have been inside the experience long enough that the novelty has worn off. What remains is something steadier, a respect maybe, or a familiarity that doesn't require amplification. They know this place in a way that takes years to develop. They also know that knowing it is a process with no clear endpoint. Because Yellowstone doesn't resolve. It doesn't offer conclusions. Every answer it gives is partial, contingent, accompanied by qualifications. The scientists who study the volcano will tell you that the risk is real, but the probability of catastrophic eruption in any human time frame is low. And then they will tell you that the system surprised them last year in a way they didn't anticipate. The biologists will tell you that the ecosystem is resilient, and then they will show you the data on the whitebark pine and the cutthroat trout and the changing snowpack, and the resilience will seem less like safety and more like effort. The rangers will tell you that the park is well managed and the risks to visitors are well understood. And then they will tell you about the person who died in 2016 and the boardwalk that needed emergency repositioning in 2003 and the geyser that erupted last month in a way it hadn't done in living memory. There's a quality to the place that you feel most clearly at the edges of experience in it. At the edge of sleep, in a backcountry tent, with the ground slightly warm beneath you, or at the edge of vision, where the steam obscures the far side of a basin, and the shapes of things become uncertain, or at the edge of hearing where the infrasound sits, just below the frequency at which you can consciously process it. At those edges, Yellowstone stops being a park and becomes something else. Something that doesn't have a good name in the vocabulary of tourism or geology or conservation. Something that you carry home with you and that changes, slowly, the way you relate to the idea that the world is stable, that the ground is solid, that the landscape is finished. The Yellowstone River in high summer carries a particular shade of blue-green that is characteristic of glacially and thermally influenced water. In the deep canyon, the color shifts with the time of day, pale and almost silver in the early morning, intensifying to a vivid teal in midday, then taking on amber tones in the late afternoon as the canyon walls catch the low-angle sun and throw warm light back at the water. The contrast between the colors of the water and the colors of the canyon, the bright teal against the orange and yellow of the hydrothermally altered rhyolite, is not something that photographs prepare you for. Most photographs flatten it. The depth of the canyon, the height of the falls, the sound and the color all need to be experienced simultaneously before the effect is complete. And even then, most visitors stand at the overlook for a while before speaking. There is a behavior that researchers studying the large mammals of Yellowstone have documented, and which doesn't have a clean explanation. In the weeks before significant seismic swarms, not consistently, not with enough regularity to constitute a predictive signal, but more often than chance would suggest, certain animals in the park have been observed moving in patterns that differ from their baseline behavior. Not dramatically, not in a way that would catch the eye of a casual observer, just a slight shift in the timing of movements, or a change in which areas certain individuals choose to occupy. The data is not strong enough to draw conclusions from, but the pattern is real enough that researchers take note of it. And the question it raises, whether the animals are responding to something in the environment that precedes the seismic activity, and if so what, doesn't have an answer yet. The geological history of the area doesn't just go back to the 3 caldera-forming eruptions. It extends much further. The mantle plume that now sits beneath Yellowstone has been active for at least 17 million years, and the evidence of its ancient path across the continent can be traced in the volcanic and tectonic record from Nevada northward, through Oregon and Idaho into Wyoming. Some of the features along that ancient path are among the largest volcanic structures on the North American continent. The Snake River Plain itself, a wide, flat corridor through southern Idaho that looks nothing like a volcanic landscape to the untrained eye, is the scar left by the passage of the hotspot. It is an enormous igneous province, buried now under sediment and farmland, identifiable only from the geophysical data and the occasional exposed outcrop. It is the track of something moving slowly under the continent, leaving devastation that has since been filled in and grown over and forgotten. What Yellowstone holds is not mystery in the cheap sense, not secrets that would disappoint you if revealed. It holds genuine unknowns, the kind that the best minds have been working on for decades and are still working on, the kind that require instruments that don't yet exist, and techniques that haven't been developed, and data that won't be collected for years. It holds things that happened long before humans arrived to observe them, and things that will happen long after the current human presence there has ended, whatever form that ending takes. The lake will keep tilting. The caldera will keep breathing. The animals will keep finding the places where underground heat warms the ground through winter. The microbes in the springs will keep doing what they have done for millions of years, in the darkness and the heat, without any awareness that they changed biology forever. There is something clarifying about a place that operates at that scale, a place where the questions don't have tidy answers, where the ground moves in ways that take decades to measure, where the oldest living things are in a hot spring, and they don't know they're alive in any sense that humans would recognize, where the most significant event in the history of this part of the continent happened 640,000 years ago, and left marks that you can see from a parking lot if you know how to read the landscape, where the next significant event might be 100,000 years away, or might be something smaller and more immediate that the instruments will see coming, maybe, if there's enough lead time. The uncertainty is not a failure of science. It is an accurate description of how complex systems work when you are living on a small piece of one of them. The ranger Jeff, who felt the vibration in his legs before the instruments registered anything, he eventually left his position at the park and moved somewhere quieter, by choice. But he said that he thinks about the park often. Not the dramatic things, not the geysers or the eruption probability or the thermal deaths that the internet articles focus on. He thinks about what it felt like to stand in the Norris Basin at 5 in the morning before the boardwalks filled with visitors, with the steam rising around him and the ground warm underfoot, and the sound of the features all around him, and the feeling of being inside something enormous and patient and completely indifferent to his presence, something that had been doing this for a very long time before he arrived, and would be doing it long after he was gone. He said that feeling stayed with him, not as something frightening, as something true. He said it didn't make him feel small exactly. It made him feel accurate, the right size, like the world had shown him something true about proportion, and he had been paying attention when it happened. Like the experience of being in that place at that hour, with the ground vibrating slightly and the steam moving around him, had given him a more honest sense of where he stood in the order of things. Not lesser, not insignificant, just correctly sized, just appropriately temporary. He said there are worse things to feel. That might be the best description anyone has given of what Yellowstone actually is. Beneath all the geology and the biology and the history and the risk assessments and the visitor management statistics, a place that puts you at the right size, a place that makes you aware that the ground beneath you has a story that started before you arrived and will continue after you leave, and that the best you can do is pay attention while you're there and not step off the boardwalk and listen for the sound that comes up through the soles of your boots and understand that what you're feeling is real. The engine is still running. It has never once stopped. And somewhere below the meadows and the rivers and the ancient bison trails and the layers of volcanic ash and the deep magnetic memory of the rock itself, it is running still. Patient, enormous, and entirely unconcerned with the question of whether we understand it. The Lamar Valley, in the northeastern corner of the park, is the place that serious wildlife watchers return to year after year. It's a wide, open, glacially carved valley with a river running through the bottom and forested ridges on either side, and on any given morning in winter or early spring, it holds more large mammals per square mile than almost anywhere else in the lower 48 states. Wolf packs patrol the valley floor. Grizzlies emerge from the tree lines in spring. Herds of bison move through in numbers that have not been common anywhere in North America for more than a century. People drive out before dawn and park along the road and set up spotting scopes in the dark and wait for the light to come up. They've been doing this for years. Some of them have driven from other states specifically to stand in the cold and watch a wolf pack cross a frozen river in the early morning. They describe it as something they can't stop doing. What draws people to the Lamar Valley so reliably is not just the wildlife itself, but the way the wildlife behaves in an environment without meaningful human pressure. The wolves in the Lamar don't treat humans as neutral fixtures. They are aware of the people watching from the road, but they have also learned across generations of living in the park that the people watching from the road are not a threat. The result is a kind of proximity that is unusual. Wolves going about their lives, hunting and playing and moving and resting, within clear view of people who are completely irrelevant to whatever is happening. Watching it, you get a sense of what predator behavior looks like when it is not distorted by human persecution. You see the full behavioral vocabulary of an animal that has been operating without interference long enough to show you who it actually is. The greater Yellowstone ecosystem, the broader landscape surrounding the national park, which includes national forests, wilderness areas, and other federal lands, covers approximately 22 million acres. This is one of the largest intact temperate ecosystems in the world. The park itself, large as it is, represents only about 10% of this total. The large mammals that use the park, grizzlies, wolves, elk, bison, pronghorn, move across this broader landscape seasonally, crossing park boundaries and entering areas with different management regimes. The ecosystem functions as a unit, even though it is managed as many separate pieces. The animals don't follow administrative boundaries. They follow the grass and the snow and the heat and the predator pressure and the routes their mothers taught them. One of the more quietly extraordinary things about Yellowstone is what happens underground near the geothermal features in winter. The soil temperatures in the active thermal zones remain elevated year-round, which means that even when the air temperature is 40 below and everything above the surface is buried under snow, the ground in certain patches near the features is warm and bare. These patches, sometimes just a few meters across, sometimes larger, exist as islands of biological activity, surrounded by an Arctic landscape. Insects remain active on them through winter. Plants that would be dormant everywhere else continue to grow in slow, minimal ways. The thermal patches are, in the ecological sense, refuges, places where life continues through the season when almost everything else has gone quiet. Researchers studying the geochemistry of Yellowstone's thermal waters have found that the chemical signature of different features can be traced back to specific deep sources, almost like a fingerprint. Water that emerges at the surface has passed through different rock types and at different depths and at different temperatures on its way up, and each of those interactions changes its chemistry. By analyzing the dissolved minerals and gases in a surface feature, researchers can make inferences about the underground pathway the water has traveled, how deep it went, what rock it encountered, how long ago it fell as precipitation and began its descent into the system. Some of the water reaching the surface today fell as rain or snow thousands of years ago and has been traveling through the underground hydrothermal system since then, slowly heated, slowly mineralized, slowly rising back toward the surface. The spring you're looking at may be returning water that was rain before the Roman Empire existed. The concept of geologic time is something most people accept intellectually, but very few people feel in any visceral way. Yellowstone is one of the few places where you can come close to feeling it. The evidence of events 640,000 years old is not buried or hidden or visible only through instruments. It's in the shape of the landscape. The caldera rim is right there, defining the horizon when you look in the right direction. The ash deposits from the ancient eruptions can be seen in roadside exposures and canyon walls. The obsidian cliffs in the northern part of the park are raw volcanic glass, the remnant of a lava flow from roughly 180,000 years ago. Not the caldera forming eruption, just one of the smaller eruptive episodes that has happened between the big ones. Standing next to that obsidian, which is black and glassy and still sharp enough to cut, it becomes briefly possible to hold the length of 180,000 years in mind. Briefly. Then the moment passes, and you're back to thinking about whether the parking lot will be full when you return. There is a research drilling program that has been proposed and in limited forms partly executed to obtain core samples from deep within the Yellowstone hydrothermal system. The scientific rationale is compelling. A core from even a few kilometers below the surface would contain a physical record of how the system has changed over thousands of years, in temperature, in chemistry, in the biological communities that have lived in it. The practical challenges are significant. Drilling into a highly pressurized, extremely hot hydrothermal system is technically difficult and carries risks that require careful management. But the data such a core would contain is not available from any surface measurement. It would be, in the most literal sense, a record extracted from the interior of a living geological system. The researchers who have worked on the proposal describe what they might find with a kind of careful excitement, the language of people who have thought very seriously about a question and have a good idea of how interesting the answer might be. The acoustic environment of the geyser basins is something that audio researchers have studied, and that general visitors almost always underestimate until they're in it. The combination of sounds, the hissing of fumaroles, the deep gurgling of mud pots, the sudden rushing roar of an active geyser, the low, persistent sound of steam rising from dozens of small vents simultaneously, creates a layered, complex soundscape that changes constantly. Sound ecologists who have recorded in the Norris Geyser Basin describe the recordings as some of the most sonically rich environments they have encountered anywhere. The sounds are not random. Each feature has its own signature. Researchers who have spent enough time in a geyser basin learn to identify specific features by sound alone, the way a person can identify familiar voices in a crowded room. The basin speaks in a specific vocabulary, and with time you begin to hear it. The relationship between the Yellowstone system and the regional water supply is another aspect of the park's significance that extends far beyond its boundaries. The rivers that originate in Yellowstone, the Snake, the Yellowstone, the Madison, the Gallatin and others, are major tributaries of larger river systems that supply water across significant portions of the American West. The water that falls as snow on Yellowstone's highlands and gradually enters the groundwater and river systems doesn't stay in Wyoming. It travels. It enters irrigation systems in Montana and Idaho. It eventually reaches the Columbia River or the Missouri River. The geothermal system influences this water, changing its chemistry, heating it, filtering it through rock, in ways that affect the downstream water chemistry in ways that are still being fully characterized. The park is a headwater. What happens in it moves outward through the continent's water systems. One of the first things that strikes researchers who come to Yellowstone from other volcanic systems around the world is how accessible the hydrothermal activity is. At other major volcanic systems, Kamchatka in Russia, the Taupo volcanic zone in New Zealand, certain areas in Iceland, The hydrothermal features exist, but access to study them is often difficult, remote, or politically complicated. At Yellowstone, you can drive to within walking distance of features that would be considered world-class scientific resources anywhere else on Earth. The boardwalks put researchers and tourists alike within meters of active thermal features in a way that would be impossible in most other analogous environments. This accessibility has made Yellowstone the most intensively studied large hydrothermal system in the world, and the depth of the data available from it has allowed for modeling and understanding that informs how we study volcanic systems everywhere else. Yellowstone is, in a real sense, where we learned how to read the language of supervolcanoes. There is something specifically disorienting about the experience of standing at the edge of a large, clear, hot spring at Yellowstone, the kind of pool that looks deep and still and beautiful and is all of those things, and knowing the temperature of the water. The visual information says one thing, the measured reality says another. The pool looks like it should be swimmable. It looks like a place to swim on a hot day. The blue is the right blue. The clarity is the right clarity. The size is the right size. Everything about the visual information is misleading in the same direction, and knowing this doesn't make the visual information feel different. You still see a pool. You still feel on some level the pull toward it that you'd feel toward any water on a warm day. And the gap between that instinct and the knowledge of what the water would actually do to you in seconds is one of the stranger cognitive experiences the park offers. It makes you distrust your own perception in a useful way. The springs that glow blue do so because of the way water absorbs and scatters light, the same physics that makes the ocean appear blue. At hydrothermal spring temperatures, the scattering is enhanced, producing a color that is more intense than the ocean's blue. The microorganisms living at the cooler margins of the pools absorb certain wavelengths and reflect others, adding the orange and yellow and green bands that make features like the Grand Prismatic Spring visible from satellite imagery. All of this is physics and biology. All of it is explicable. And all of it still looks, when you see it in person, like something that was created to be looked at, something intentional, something curated. The natural world at Yellowstone has a way of producing effects that feel designed, which is unsettling in a specific way. Not because you believe they are designed, but because your brain keeps registering the design even after you've explained it away. The management challenges at Yellowstone extend into territory that has no good precedent in the history of protected areas. How do you manage a geothermal system? You can't fence a geyser or prevent a hot spring from expanding or contracting based on underground pressure changes. You can only watch, document, and respond. The infrastructure that serves millions of visitors, roads, utilities, buildings, sits on top of a dynamic geological surface that changes the rules without notice. Road maintenance at Yellowstone is complicated by the fact that the ground the roads sit on doesn't always stay where it was when the road was built. Sections of the Grand Loop Road have been closed and rerouted multiple times, not because of weather damage or wear, but because the ground beneath them deformed, because the thermal activity shifted, because what was stable ground last season became something else. The Park Service manages infrastructure on a surface that is actively, measurably moving. There is a school of thought among some geologists who study the park's long-term history that suggests we may currently be living in a period of relative quiescence within the hydrothermal system, that the current level of activity, while dramatic by the standards of any other landscape, may actually be lower than it has been for significant periods in the past. The evidence for this comes partly from the geological record of ancient thermal features and their extent, and partly from modeling of what the system would look like if the heat flux were higher than current measurements suggest. This interpretation is contested. Other researchers look at the same data and read it differently. But the possibility that the Yellowstone we see today, already extraordinary, already dangerous, already beyond easy comprehension, may be a quieter version of what the system is capable of doing on a sustained basis, sits uncomfortably in the mind once you've heard it clearly stated. The park closes to through traffic in winter, but it never closes entirely. Snow coaches and snowmobiles carry visitors to the major thermal areas. Rangers stay through the winter months. Researchers continue their work, and the geothermal features, indifferent to season, driven by forces that operate on timescales where the difference between July and January is trivial, continue as they always have. The geysers erupt into air that is cold enough to turn their columns of water to ice crystals before they fall back to Earth. The hot springs steam more dramatically in winter because the temperature differential between the water and the air is greater. The mud pots freeze at their edges but remain liquid at the center, where the heat from below keeps the temperature above freezing regardless of what the atmosphere is doing. In winter, Yellowstone looks most clearly like what it is, a volcanic landscape that the climate has no real authority over. The cold is just a surface condition, the heat is geological, and geology wins.